good afternoon to everyone joining from here in Europe and from Israel, and good morning to all our participants from the States. I welcome you all to the second day of the 2021 International Online Groningen Symposium on Digital Paleography and Hebrew Aramaic Scribal Culture. We had a wonderful first day yesterday. It was great to see all the presentations, the discussions. We had a great participation from everyone. So thank you very much for that. We also look forward to see more exciting ones today. So my name is Maruf Dhali. I'm a PhD candidate from the ERC project on the Dead Sea Scrolls. I will be chairing today's first session on digital paleography. So we'll follow the same structure like we did yesterday. We have three amazing speakers in the first session, all of whom are famous and known by their names. So Lambert Schomaker, Peter Stokes, and Nachum Dashuis. So our first speaker today is Lambert Schomaker. He has been a professor of artificial intelligence with the University of Groningen since 2001. Lambert received his master's degree in psychophysiological psychology in 1983 and his PhD degree in simulation and recognition of handwriting movements in 91 at Nijmegen University in the Netherlands. Now, since 1988, he has been working in several European spirit projects concerning the recognition of online connected cursive scripts on the basis of knowledge on the handwriting movement process. So in recent years, in 2015, he became the co-chair of the Data Science and System Complexity Center at the Faculty of Science and Engineering. In 2017, he joined the Cognigron, the Center for Cognitive Systems and Materials, in a large-scale 7-year project in neuromorphic computing. He is known for research in simulation and recognition of handwriting, writer identification, style-based document dating, and other studies in pattern recognition, machine learning, and also in robotics. Also, the thing I mentioned yesterday, he designed the Monk system, an interactively trainable search engine and an e-sign service for historical manuscripts. So on a personal note, Lambert is my direct supervisor, and I'm working with him for almost 5 years now. So what, in really short, what amazes me most about him is how thorough, resourceful, and insightful he is in every topic that we ever discuss. And yet his modesty surprises me. So it is amusing to listen to him every time. So I now welcome Professor Dr. Lambert Schomaker to talk on the dilemmas in applying AI methods in digital paleography. Lambert.
Thank you, Maruf, for this very nice introduction. I hope that everyone can see my screen.
Yeah, we can see it, Lambert.
Okay, thank you. Yeah, so dilemmas in the application of AI methods in digital paleography. So this is my overview. I will talk briefly about successes in what is called AI today, but which is in fact a very narrow area within AI, which is deep learning. Then I'll talk about some caveats on these massive parametric methods in the view of limited size data sets. And I think that what might be interesting in this conference, also given the fact that we have this Isaiah Scrolls paper out now, is to talk about the choices we made in the Scribal Culture's ERC project. And finally, I will talk about trust or explainability, yeah, because everyone talks about explainability these days, and well, we'll get to that later. Yeah, so what is going on at the moment is that already for several years now, quite long, it started around 2013, 2015, new approaches of training neural networks became famous. I first started doing neural networks in 1986 after the Rumelhart and McClelland book. They had a diskette in the back with C code, which was of course fantastic. Then there was some waxing and waning of neural network research. There were some problems and limits, but starting at around 2005, the new methods for training neural networks were invented. Some aspects already existed since 1990, especially the convolutional neural network idea. I'm not going into the detail, but it's as old as 1989. Jan LeCun, now at Facebook Research, was introducing them for handwriting, because handwriting is such a nice and difficult problem. But yeah, the incubation time was more than 10 years, and for a very long time, Jan LeCun was the only one being successful with convolutional neural nets. But at the moment, even in master project with students with very limited domain knowledge in any of the domains we are talking about, biology or paleography or whatever, they have very huge successes. So these are a few examples. Jonathan Maas did something about mutant, non-mutant classification on the microscopy images, which was really, for the first time in my life, 100% accurate, even when the data was from another biologist, from an analyst in the lab. We had Tim Oosterhuis doing self-driving cars with the question, can you track the instances of the cars around you, not just classifying a car as a class of cars, but just the blue Ford that was just driving to the left of me, and so on. Also very high performances, and the 97% is if you have a good camera. Sheng did a lot of work in the Chinese OCR, for instance, very good results, and so on. In brief, I'm not going into the detail because of time, but you see all kinds of high performances, also indicating that we are working on deep learning, right? And then one of the reviewers of the +1 paper said, well, you're not doing that much of AI in this paper. Which well, of course, if you're a little bit competitive, that is a kind of a provocative remark. Also, in view of the fact that that Maruf had been doing deep learning in the binarization stage. So to give an example of the deep learning papers that I'm also involved in with Sheng He, there are several of them. In pattern recognition, for instance, using a dual task learning on single words. Then we have the FragNet approach, which is also is now made available on GitHub, the Python source code for this approach, taking a whole word and fragments of words to get to the writer identification. And then this year in pattern recognition, again, there will be a new paper using recurrent neural networks for writer identification. Yeah, so this is a little bit of my dilemma. We are doing deep learning, so a reasonable question is, why aren't you using that in the ERC project? What is behind that? Now, first of all, we can see that these type of publications are done with really massive data sets. So, for instance, 99,000 selected word images, so that you have an ample amount of images for training. Data sets with 657 known different writers, several of them producing more than full pages of handwritten text. And so these academic benchmark data sets are really very large. And anyone in this conference will realize that although the number of scans, for instance, in the Braille collection or in the IA collection is large, the amount of annotated and detailed annotated data, whether you talk about the date or writer identity or even textual content at the level of the image. I mean, the texts are transcribed, but when we asked for, let's say, the regions of interest being labeled, then in the ERC project, this proved to be quite a difficult thing. So yeah, from the data requirement point of view, we are in trouble already if you want to apply deep learning. And now I'm going to do something extremely risky, but it is very visual, so don't worry. I'll go as slow as possible given the time. But I do like you to understand something fundamental about estimating models. So let's take the simplest of models, which is the linear function. I have one input, x, and I have one output. Yeah, so we can see that y equals some factor a times x plus some value b. So we have two coefficients. Yeah, in neural network terms, you would say weights. I have an offset level b, and then an amplification factor a, and I multiply a with x, and then I add b to it, and then I have a nice linear function. the input is X, the output is Y. Yeah, so I think this should be manageable. Then the reasonable question is, how many measurement pairs of X and Y's do I minimally need from a data set to estimate those weights or those coefficients? And the answer is 2 pairs. I need 2 points in the plane, x1, y1, and x2, y2 as examples. And before you get really too stressed, I will go to a visual representation. So here we see a 2-dimensional plane with x on the horizontal axis and y on the vertical axis, yeah, which is the function of x. And here we have 2 arbitrary examples that I just give the red points. And now I want to find this equation. So I'm not going into the detail of getting at them, but you can see that the very simple, even let's say high school or sub-high school level computing is done here.
Help, help.
Yeah, but the message is, after this, we know all the values of the function for x, being given just 2 points. And now the question is, what would happen if one of the example points is lacking? Yeah, so first I had 2 points. Everyone can imagine that you can draw a line through this and do some little computing, and then you get the function. But now I remove one of the example points. And it's interesting what happens now is because now suddenly I have an infinite list of possible straight lines that I can fit through this single example, right? And that is really worrying. Yeah. So this is at the lowest level, at the simplest of models, is an example of what happens if you don't have enough data. It means that your solution space is not constrained enough. Yeah, and this is why we in machine learning are so greedy about the data. Because and now we can now I'm going to be also critical of people in my own discipline, right? So because if you see that you need 2, if you have 2 parameters, I need 2 input-output pairs. Then if I have 1,000 parameters, how many examples do I need? Of course, 1,000. And if I have 1,000,000 parameters, you get the drift. Yeah, so the more complicated your model, the more examples you need to constrain the solutions. Otherwise, you get into the situation of multiple solutions. And now we get into the worrying part, right? Some deep learning models have hundreds of millions of parameters and very often not enough data. There's a very famous model in AI at the moment, GPT-3. It's based on text. It can do text predictions. It can even generate poems. It can write little programs in Python, which is also text. It's just absolutely fantastic. The training set is about 500 billion tokens, and it has 175 billion parameters. Well, at first sight, that looks nice because at least I have more data points than coefficients, but you still have to realize that this is really not enough. There was one person at Google critical of this, and but she was fired, yeah, because because there are some religious aspects to this deep learning. But I can guarantee you that even yeah, if you have 3 times as many examples as coefficients, then there are problems, and they are called overfit. I'll get to that a bit later. So now what's going on in neural networks is the following thing. That when Newton did his work, he was living in a maybe complicated but also still simple world where the landscape was for the equation that he wanted to solve was simple, right? But for these very complicated problems, we have a performance landscape that may look like this. It is fictitious, but I want to show you what is going on if you have trained a particular neural network. So on the vertical axis, we have the error that a model makes, the loss. So the error should be low, yeah? So we should be in the lower points. And there we see the solution points, solution 1, solution 2. So, surprise, surprise, there are several solutions, and they may be very comparable in performance. And if I vary some coefficient value W, then I may end up in this kind of solution. So the question is, which one should we take? The most simple solution would be to say, for instance, let's take the deepest point, maybe here solution 4, because that's a very, very deep ravine or ravine. I don't know what the pronunciation is. So it's a very deep one. But there may be other criteria that more experienced neural network people know, is that maybe it's better to have a solution like solution 2, which may be slightly worse, it's slightly higher, but it's not so sensitive, because here the bowl shape of the landscape, of the loss landscape, is more smooth. And so instead of having one solution, we have multiple solutions. And so we enter the following problem. So reasonable solutions. Would this be acceptable to scholars who are trying to solve a single question? Yeah, it is a little bit complicated, I think. Mathematically, this state of affairs is called ill-posed problems. And the ill-posed problems are problems for which there is no solution. Well, we can disregard this one for the moment. Or there are multiple solutions. Yeah. So in mathematics, this situation is, I mean, in hardcore mathematics, people also don't like neural networks for this reason, also for several decades. Yeah. But we can try to do some countermeasures. And the countermeasures, I already mentioned them, is to constrain the set of possible solutions by giving a massive amount of example pairs of input and desired output. And the other, of course, is to simplify your model so that the number of weights or coefficients is much, much smaller than the number of examples. So let's go to modern deep learning. Yeah, now so what happened in deep learning is that we have many ways. The dropout trick was just mentioned just before the meeting. Yeah. All kinds of tricks, like the Adam trick of the learning rate. We have dropouts, we have the mini batches. There's a lot of tricks. I'm not going into the details. I'm just mentioning them to show you that I know a little bit of what I'm talking about. But what is new is the ability to pick a reasonable or good solution out of the set of many possible neural network solutions. This is what has improved a lot. Still, a lot of data is necessary, because also we have noise. Yeah, that's just a very problematic case, especially also if you look at the backgrounds in the scans that we're dealing with. In many cases of the results that my fellow AI researchers are showing, then the number of used examples is not really enough. Yeah, and then they use the dropout trick and then say, well, it works. And usually also the data is then randomly put in different bins, and then you do what is called k-fold evaluation to try to estimate the range of performances that you get from this particular data set. And if this is a little bit reliable like this, so for instance, let's say 94% plus or minus 3%, then from practical purposes, you may say, maybe we are happy with this. This is possible, right? But remember that the multiple solutions issues is still playing a role behind the screens. Yeah, and in this GPT-3 model, there are only 3 examples per parameter, and this means that it is that in the face of noise, this is very limited, and so the person who was critical of the GPT-3 model, for instance, and also others by now, have shown that in fact what such a massive neural network does is it becomes a little bit of a lookup table. It's just storing examples without generalizing and finding the general patterns. So our question is, would a paleographer, yeah, and in this terms I would like to talk not about the practical user but the scientific user, worry about, for instance, as an example, an unknown influence of an original data set or training set that you apply to your own problem. Yeah, so there is some excellent pre-trained neural network from another lab. It was trained on data that you may not know, but maybe it's the same historical period. And then you're going to make this very, say, essential scientific decision from that tool. Yeah, as an extreme example, let's say someone trained some feature methods on the basis of the Dead Sea Scrolls scans as training data, and then apply it for writer identification in the elephantine samples. Yeah, would that be worrying, or would that be acceptable? Would a paleographer worry about the fact that the neural network solution is not unique, and that comparable other solutions may exist with slightly different answers? And last but not least, this is of course the black box argument. Well, isn't it a very complicated, unclear thing that comes with a particular output? So the verdict, when we talked about well, applying techniques, when Maruf and I discussed about it, and also with the extensive discussions we had in the ERC team, probably yes, paleographers would worry about this. So these are the chosen solutions in our project. We do want to use deep learning when there is really an abundance of data, pixel data for binarization. Yeah, and at that level, there is a lot of detailed data, and you can have a robust method. And the BiNet algorithm by Maruf is an example of that. But we want to avoid it in the critical classification stage. Then we would like to minimize the number of parameters in the models by using sparse parameter methods from regular pattern recognition, which is more based on geometry than on just learning or training a neural network. You have specific, explicit geometric methods. I will give an example in a minute. And also data-driven code books, yeah, with little fraglets of handwriting that everyone can see and understand. And for dating, we use a sparse parametric regression method for dating. This will come out later. And then for the final decision making, I think we should just look at the empirical sciences like biology, physics, and also psychology, where there is a lot of knowledge about statistical testing. There is even more knowledge about statistical testing than in computer science, because computer science has its roots in formal deterministic models. So there is maybe some stochastics course in computer science curricula, but only since the advent of machine learning, really, let's say, serious statistics is becoming part of computer science. And there is a lot of knowledge in in the empirical disciplines on how to do this hypothesis testing on data. And there we use dimensionality reduction, clustering, chi-square test, and also logistic curve fitting. Yeah, so instead of having a network that maybe has a very good performance, but is risky in the interpretation, we try to take these constraints. And this is, of course, yeah, difficult. And this is why I want to talk about the consequences for us as AI researchers, because yeah, this is, let's say, just off the work floor. The consequence for us is that there is no low-hanging fruit, and we cannot easily surf on the wave of the deep learning successes in this particular work. There is limited interest by the AI community because, of course, they all want to wallow in the success of deep learning and so on. But if you choose not to use these techniques, then the interest will wane. And of course, well, but we can also take another point of view and say, maybe for the future, well, if there would be a commonly accepted reference image data set over scripts, periods, and cultures, and if that data set is really huge, maybe you could train an autoencoder, which is a particular type of neural network, I've sketched it on the top right. And if you have enough data, then you could train the system to represent the shapes in a reusable feature vector that is tapped from a bottleneck layer, as we call it, from the middle of the neural network, and that those numbers, that shape descriptor that is dropping out of the neural network, can then be used. And if the data set is large enough, you have an even spread of possible biases. So we do see solutions, but for instance, with such a concept of transfer learning that is quite popular in machine learning these days, in deep learning, is this acceptable by scholars? That you use a very large set from totally different data than your target problem to do hypothesis testing. This is, I mean, it is serious what we are doing. So, although we did work on deep learning in writer identification, we assumed that it was too early for sensitive topics such as the Dead Sea Scrolls to use deep learning here. The amount of labeled annotated data is extremely scarce anyway. How many writers are really known? How many dates are intrinsically known in the text? And I think that given this problem, we needed to work with methods that already work reasonable or good with limited amount of data, and also with methods that have a more direct relationship between the visible shapes and the computed shape features. And so the idea is that the current studies are intended to gain trust in the algorithms. So what we would like to see is that people in the humanities see this as an instrument like the microscope that is given to the biologist. I mean, the microscope did not replace the biologist. The biologist is helped by a particular tool. And you need to have trust in tools, and I'll get back to that. And so what you can say is, where is this road to this deep learning Eden? Yeah, that is the question. And an important issue in this is explainability. Explainability is a complete hype. There is a group within AI, the people who are logic oriented, who have taken this topic as a kind of criticism. Neural networks should be explainable, and they aren't, and so on. And they get a lot of funding money, research funding for this, because at first sight you say, well, of course, techniques need to be explainable, right? I call this the fear of the black box. So the funny thing is that with neural network, you can do almost anything. So what you could do is you can train a neural network to do a particular decision, but not only give the decision, but also output an understandable narrative for this decision as text. Would that solve anything, is the question. Of course not, because with the recursive image that I have on top, you can see that overfit and ill-posedness and multiple solutions are still there also in that part. I mean, you would get, say, a textual description of the decision, but the normal criticisms with respect to the deep learning still remain. And then there is another aspect to this explainability. And what I like, I also in Erlangen, there was a conference quite a few years ago, and there I introduced the example of the blood pressure measurement in medicine. Many methods in medicine are not fully explainable, but still are used. Yeah, so the blood pressure, if you want to measure blood pressure, you need to stick a needle in a vein, and then have a very reliable transducer to give you the exact numbers. This is absolutely not what doctors are doing. And maybe it's good because there is no pain and no contamination risk. But the numbers that are coming out of this procedure are very indirect and totally different numbers from the real physical blood pressure that you would measure in, let's say, in a science-based way. And at first I thought I was the only one with this argument, but then I found out that Alex John London has a nice report in the Hastings Center reports. He's a professor of ethics and philosophy, and he makes the following point. Just as Aristotle's empiric succeeds in promoting health by prescribing chicken for a healthy diet, even without knowing why chicken is a healthy food, and modern clinicians prescribed aspirin as an analgesic for nearly a century without understanding the mechanism through which it works, and then lithium has been used as a mood stabilizer for half a century, yet why it works remains uncertain. And yeah, so let's also agree that this whole idea of explainability is nice. Who could be against it? But there are very serious disciplines where you can take this with a grain of salt. How often do you like to look under the hood of your car for explanations while driving on the highway? You just trust the engine. What if such an explanation takes 20 pages? I mean, there is no magic in neural networks. You could really write out in a very long computer print what exactly happened from neuron to neuron, and then trace what happens. There is no magic in it. It's computer-based. Everything is explicit, but unfortunately, the analysis of what the neural network does has become a big data problem in itself. Yeah, and so are people looking for these kind of explanations? Of course not. This kind of reasoning brings me to the point where I would say neural networks should work reliably first. I think this is the main responsibility of us as an AI researcher. The reliability breeds trust, and I think trust is a more fundamental issue than the explainability. And reliability means that we can provide guaranteed margins of error, reference data, benchmark data, and replicability of results. So, yeah, if you want to use deep learning in digital paleography, I would say make sure that you have an abundance of training examples. The examples should be from the same problem domain as the unseen target test condition, and the samples should be independent but identically distributed statistically. And this is where it's getting difficult, yeah, because if you have a new problem, of course, the data will be slightly different from what you already know. These are my conclusion slides. Yeah. I would say that in case of serious scientific questions, it's not a bad idea to revert to proven methods and try to convince scholars that algorithms are not scary. At the same time, I think it would be a pity if digital paleography would not benefit from the new highly parametric deep learning methods. And I think it's possible as long as you keep an eye on dataset biases, overfits, ill-posedness of the required mapping, and lack of data in general. And this concludes my presentation.
Thank you very much, Lambert. It was really wonderful to see the presentation. We have one question. So it's from Gidiofe, that can additional trained data be generated through complementary computational methods, for example, clustering, etc., with or without additional interpretation?
Is this, I'm wondering whether this is a question about data augmentation. So there's one particular method that is used in deep learning at the moment when you have a lack of data, that is that you yet again use another neural network to generate artificial samples in a way that generates believable samples. And this is risky because it's a self-fulfilling prophecy. And so I'm not, maybe the person who asked the question can ask the question.
What I can do is I can ask Kidi to ask some kind of, Kidi, you can turn on your microphone and ask the question.
Well, thank you very much for your talk. Now that I actually reread my question, I realized that it could be a little tricky to understand and even trickier yet to disambiguate even further. My question about the scarcity of training data comes from the fact that the little data that could be available, especially in cases of, for example, the Dead Sea Scrolls, is some analysis that had been done by scholars and not through, as far as I understand, computational methods where, say, the authorship or ID of the author or the school of the authorly schools are being clustered through some statistical analysis, but rather by a person that is familiar with these texts and familiar or is without, let's assume, any inherent biases. And my question is, can computational methods that are not based on neural network help in generating additional training data that, for example, a scholar that is not using them would not have noticed otherwise?
Yeah, so this you get into the area of semi-supervised learning. In fact, in the Monk system, we heavily rely on this. So we use standard featural methods to group data. So then you get a hit list, and then the users can confirm or disconfirm the correctness of the samples that pop up in such a hit list. So yes, it is possible to do this, and what we see is that if you get a critical mass of examples, then suddenly the quality of this data mining process has a steep increase in performance, and then stabilizes again to what is maximally attainable with this number of examples. There's an other aspect that in the ERC project did not completely work out yet, because I think it requires more interaction between AI researchers and the humanities. And that is that we repeatedly, Maruf and I said, look, classifying into dates or in writer identity is possible, but we can do much more. So if you have an idea of an attribute of the shape of the text, if you are using names for the appearance of shapes of characters, or even the layout of the page, etc., anything that you could say about the sample will help, because in fact neural networks even work slightly better if you have a multidimensional output in terms of several attributes of a handwritten sample than just this 1 out of n classification, like in writer identification. And this proved to be very difficult, not only within the ERC, but also in general, because of course there's a lot of discussion going on in paleography about is there consensus about essential attributes, yes or no? And my answer would be, if you have some consensus that over a website you can ask people to do something similar that like Peter Stokes has done in DigiPal, then that will help a lot. So anything that the human brain can add to the natural data or the image data in terms of symbolic tokens or attributes in textual form, or tags, as you would say in Twitter times. All tags are useful.
Giri, is it okay, or do you want to discuss further? We have 1 more minute if you want to add something else.
Well, thank you very much for the answer. I obviously have a few follow-up questions, maybe the shortest of which was there any consideration to implement additional elements, as you said, to the multidimensional analysis, such as NLP, for example, to actually go for the context as well as the additional parameters?
Yes, that is a very interesting question. One of the underestimated problems is the following: that you have a transcribed text. So you have the page scan on the left, and you have a transcription on the right. And a lot can be done with neural networks these days, but in our experience, it still is very difficult to find the correct association between let's say the text objects in the visual domain, and then this kind of canonical, or say target nicely formatted machine printed text, or encoded digital text on the right hand side. A lot is possible these days, but it's all very ad hoc, and only in the cleanest layouts you can do things. But we have a course in handwriting recognition, and we asked the students, several cohorts even of students at the master level, to do more of this, say, contextual and content-based analysis. And yeah, the Dead Sea Scrolls are beautifully difficult still in this respect, still challenging.
Yeah, thank you, Lambert. The time is up, but I'll still take one quick question from Daniel Stockel. So Daniel can ask the question. So it is about rider identification. And Daniel, if it is okay, you can talk. Yeah.
Okay, very quickly. Many thanks, Lambert. What is the minimum size of the fragment with regard to letters that you need for your analysis now? In the past, you mentioned 100 characters. Maybe this has changed. And did you combine in your analysis different fragments, assuming they were written by the same scribe, or didn't you do that at all? Thanks.
No, the fragments were all lumped into a very big pile, and the size of the fraglets should be larger than the kernel size of the hinges. Yeah, because the goal of the fraglet approach is that you have structural elements in the pixel space, in the pixel representation, like loops and crossings and the more complicated elements. If they are too big, you could say, then you get into the full characters. And indeed, if you look at our code books, some of the fraglets, in fact, are simple full characters. But let's say, if I would say kind of, let's say, a rule of thumb is something like a third or a quarter of a normal letter would be a nice size for fraglet-based approach. Yeah, because then you have also this aspect of compositionality, that combinations of fraglets then can in fact give the evidence away that the particular character shape is full character shape is there.